Okay, we're going to start to look at interference at the stage 2 level now. So a quick recap on waves first of all. If you look at a wave there, you've got to remember that there's a crest to that, there's a trough, and a wavelength would be from the distance between consecutive crests like this, or the distance between consecutive troughs. So that's your wavelength lambda, and you've also got the wave equation V equals F lambda. So that's the basic stuff you've done before. The other stuff you've done before was this idea of diffraction, which was the change in direction of a wavefront when it encounters an obstacle or goes through a slit. So when you've done this before, we've talked about it bending as we've gone through there. And there's no change in the speed or the wavelength here. So the wavelength stays the same. So if you picture a wave coming through here, like this is a wavefront, plane wavefront. As it encounters this obstacle here, this will actually go straight ahead still, but at the edge here, it'll come in behind that obstacle and bend. So you get a bending there in behind that obstacle there. Okay. Now if you have it on both sides there, as in the case of slit, you're going to get it bending in both directions there. So a slit would look a bit more complicated. So in the case of a slit, you would actually get this going in both directions. Okay, relatively straightforward through the middle where most of the wavefront's going there, but at the edge it's going to occur in both directions. And it's important that the slit is a similar sort of size to the wavelength there. If it was lots and lots of times bigger, you wouldn't get much diffraction at all at the edges there. So if you close that up, you'll get it going more circular in fact. So if the shape was more like this, that sort of size slit, you would find this would become a bit more circular in fact. Okay, more random. So you get good diffraction or changing of direction of the wave, or bending of the wave, as it encounters an obstacle or goes through a slit. So it's the change in direction of a wavefront when it encounters an obstacle or passes through a slit. And it's going to be a similar sort of order as the wavelength. Other things to bear in mind are the terms monochromatic, which means one, and chrome means colour. So monochromatic light is a good thing we're going to use for interference experiments. The better term for it these days at the stage 2 level is to think about it as being the same frequency or one frequency. Alright? So we want sources that have the same frequency there. So you could actually approximate that in the lab by using a sodium lamp, which has got a yellow colour all the way through, and the two frequencies in the sodium lamp are very close together, so that's very close to monochromatic. You could use a laser source there, and that's pretty much got the one wavelength, one frequency. Okay? And you could also do a white light source with a really high quality filter to try and approximate that experiment as well, where you want monochromatic light sources. The other term is coherent light sources, or coherence, and that talks about them being matching essentially. You want the waves to be matching in frequency and have a constant phase relationship and be the same type of wave. So that's the coherence one. Now that's quite complex to understand. We're going to look at some examples how to actually distinguish what is coherent and not coherent later on. So we'll come back to that one. So another thing we've looked at is interference as well in the last video. So the idea that when one wave passes through another wave like this, of the same type like this, if they pass through each other and they happen to be meeting crest and trough like this, what you're going to get here, at this particular point is here, you're going to get constructive interference where they add together to form a large wave, okay? And that's constructive. So if they meet in phase, you'll get constructive interference at a point. If they meet out of phase, where one's sort of meeting like this and meeting one like that, you'll get destructive interference where they add together to give you no wave through there. It's a bit rough, that one there. So destructive, okay? So you can get a pattern of constructive and destructive interference by using two sources. Now we've done this before last year, this idea that you have a yellow wave source or sound source here goes to two slits or two sources. When it's coming through here, you should find that in the middle here you're getting this bright band or a loud sound or a big wave, and you see the big wave is there. And the reason for that is that what's happening here is you've got waves coming out of here, going to a point, waves from there going to the point, and because they're actually coming through matching, they're coming out matching here, you see two crests here or two yellow lines here, because they're matching there, when they arrive they travel the same distance. So if they leave matching and they arrive matching, you're going to get constructive interference there. You're going to get a nice big bright band or a big wave or whatever. At this point here though, just here, one travels further than the other. And the one that's travelled further here, about this much further here, might actually travel a half a wavelength further. And if it travels a half wavelength further, it's a half wavelength behind. And don't forget, this is a continuous wave source here. So is this one. If it's a half wavelength behind the other one when it arrives, you're going to get, compared to the other one, this one arriving like this. So the other one's going to be slightly ahead, so that's going to have already arrived as a crest there, and then the trough is coming through. So that trough meets with this crest, which means you're going to get them meeting like this, and you're going to get destructive interference at that point there, which is why you get that minimum. And you can see it goes max or minimum, or if it was light, bright, dark, okay? And you get this two-slit interference pattern, or two-source interference pattern there from the lights. If you switch this to a different colour, by the way, the pattern is different. So if you try doing say a blue one there, get in blue, you try this again, you can see you've got 1, 2, 3, 4, 5 maximum there. If you try it with blue light though, which is a shorter wavelength there, or higher frequency, the pattern is 1, 2, 3, 4, 5, 6 and a bit more. So you're looking at slightly narrower bands there, okay? So they're closer together as bands. So if you had lots of colours coming through, you get a mixture of lots of these interference patterns on top of each other. It'd be very hard to pick out, okay, if you were using white light. That's why we prefer to use monochromatic light. So let's just look at this idea of coherences again. It's definitely monochromatic because we're trying to use light here of one frequency. We're using the yellow frequency here. To get it coherent though, we've got one source here sending matching waves to these two slits. So that when the waves leave these slits here, they're coherent with each other because they come from the same original wave. That's really important. And so this would definitely be coherent wave sources because they're actually in phase with each other perfectly. But to be coherent, they just have to maintain the same phase relationship. It doesn't have to be an in-phase relationship. So you could actually move these slits up there or down so that they were further away. And let's say the slits are actually further down here now, and they were like that when the source came to there. Now this one has to travel a bit further here. And if it was a half wavelength further to get to this lower slit, they'd now be coming out of phase compared to this one. Okay? Would you still get an interference pattern? Would these still be coherent? And the answer is yes, because they're still going to maintain the same phase relationship. They've still got the same matching wave, it's just that this one is a half wavelength behind the other. Okay? So what would happen here is a pattern, you'd still get a pattern, but you would get it in the opposite phase here. So you get it going like that. Okay? So that's the best way I can think of to sort of explain coherence. It is okay that they're out of phase as long as they maintain being out of phase all the time. This one will always be out of phase compared to that one, so therefore it's coherent. And it came from the same matching wave of frequency and the same type of wave. So it's still coherent. Alright? So key points to be aware of then. Now you've got monochromatic light, which is made up of one colour, but it's defined more specifically as light of one frequency or one wavelength. It's better to describe it actually as a frequency because the wavelength can change with different media. So frequency is a more fixed value, so it's one frequency. Sometimes you only get a narrow range of frequencies, you can't get exactly one, but that'll be a monochromatic light. Some examples of how you could do that in a lab, or try and get close, would be to use a sodium lamp or a laser or a white light source with a very good quality filter that just lets one colour through, essentially, and you can see interference patterns. Don't forget phase means being in step with each other, so if wave sources are in phase, they're in step, they both emit the troughs at the same time, or both emit high electric fields at the same time. Coherence is when they maintain a constant phase relationship. They've got to try and keep or maintain a constant phase relationship. So if they're in phase all the time, they'll do that, but they could also be out of phase all the time, and that would also achieve it, as long as they maintain the same degree of relationship of phase there. Don't forget it needs to be the same frequency and the same type of wave when you do that. Okay, then you get interference patterns. So best ways of achieving that would be to use a laser or use a narrow slit in front of a pair of slits, and then you can get coherence at the pair of slits, okay? There'll be two coherent sources. Now, incandescent sources like light globes and stuff are not coherent nor monochromatic. Now, the reason they're not monochromatic is because they're going to emit a range of frequencies because you've got lots of different atoms or molecules vibrating in there at different frequencies, different rates because of the temperature there, and therefore they're going to release EM waves at different frequencies. So you're going to get a range of frequencies, so therefore these vibrating charges will cause these range of different frequencies and it won't be monochromatic. Okay? On top of that, they won't maintain a constant phase relationship with each other, all those different vibrating frequencies. So you won't get coherence either, because they're all independent with their vibrations, So they'll be in different directions of oscillation, but also different frequency rates. All right? So they can't maintain a constant phase relationship either. Now, when you're solving these questions, the key thing is to keep in mind is what's the path difference between the two waves. To decide if it's going to arrive and be constructive or destructive interference from two sources, we need to know what the path difference is doing. So we've got an example of that here. If you had two transmitting towers of radio waves, okay, and they have the same wavelength and they're actually transmitting in phase with each other, what would happen if you were trying to receive the signal at point A here? We've been told that it's 70 metres from one tower and 82.5 metres from the other. So as a general rule, you should work with path difference first for all your interference things. So the path difference here between this one and this one, which one travels further and by how much? So if we look at that, it'll be 82.5, take away 70. You get your 12.5 metres extra distance travelled. So that's step one. What is the path difference between the two wave sources to that point we're talking about on a screen, or in this case, trying to receive a signal a distance from a tower? Having done that, you need to work out how many wavelengths is that worth. So 12.5 metres, how many waves is that worth? So each wave is worth 5, so 12.5 divided by 5 gives you 2.5 wavelengths there. Now you know the number of wavelengths there, you can make a decision on whether this is constructive interference or destructive. If it's whole numbers of wavelengths, it's going to be constructive because they'll arrive and match up like this. But if they arrive a half out like that, you're going to get destructive. So in this case here we can say it's therefore it's out of phase arrival, so it's destructive interference. And that's the sort of routine you're going to be following with all the questions in your line here. It's based on that logic. What's the path difference? How many wavelengths is that? Therefore we can make a decision on whether it's in phase or out of phase.